Ngalakin kadijan nyunga boja.
Hello everyone, welcome to the second tutorial of the ELEC 4404 signal processing. I'm Lu Jin, and so today in this practical class, we are going to discuss the questions given in the tutorial 2. But before the start of this class, I want to apologize. The reason is in this week, the Monday was a public holiday, and because of the public holiday, so some classes of some units were rescheduled by the university, and one class of another unit I taught was rescheduled to 9 to 10 a.m. on Thursday. That means today. So because of this clash between that rescheduled class with this practical class, so I will not be able to cover both classes at the same time. And because that class is pretty short, so only 1 hour long, so between 9 to 10 a.m. And our class, this tutorial class between for the ELEC 404 will be 2 hours long. So I decided to cover that session between 9 to 10. And after I finish that class, I will return back to the Microsoft Teams to keep going the discussion in this practical class. So at the beginning of this practical class, I have already pre-recorded video for some questions discussion in the tutorial 2. And I'm asking another teaching staff, so Dr. Lin Zhu, to help me to play this video on Microsoft Teams so that all you students can watch this video in the first hour of this practical class. I'm sorry for this, but this is just one of rescheduling stuff. So from next week onward, everything will be returned back to normal, and we don't have this clash anymore. And just for this 1 hour, so I have to pre-record this video for this session. And sorry about that, and I hope this will not impact your learning too much. At about 10 a.m. Thursday morning, I will return back to this Microsoft Teams class, and we can keep discussing the remaining questions. If you have any problems or issues, so after I come back at 10 a.m., you can just ask me through the Microsoft Teams in our practical class. Thank you for your understanding. Okay, now let's start our tutorial 2 discussion. In this tutorial 2, we have in total 7 questions. Some of them are pretty simple, but some of them are challenging to say truth. For example, question number 4 and question number 7 may be hard for some of you, and I hope we can discuss these questions in this practical session, maybe in the second half after I come back from the other class. Okay, at the beginning, let's start from the easy questions. Question number 1, question number 2, and question number 3 are pretty simple. In the lecture of this week, we have already discussed about the situations or cases with 2 random variables in the same system, and we focused on the relationships between the random variables. Like, okay, what are the joint CDF, joint PDF, the marginal PDF, and also we learned about the correlation and covariance, so all this stuff, okay? And we are going to use this knowledge to solve some of the questions. Now let's start from the question number 1. Sorry. Okay, question number 1. So for any 2 random variables, x and y, so we know the variance of the x is the sigma x squared. The variance of the y is the sigma y squared. Okay, these 2 things are not new because these 2 variances are just about the 2 separate individual random variables. So we learned this one from the week 1. So these 2 things should be fine. The next term, so you can see we are having the sigma x plus y squared. Okay, this is sigma squared is also a variance. For example, on the right-hand side, you can say we are using VAR, which is a variance, okay? But this variance is for a new random variable, which is equal to x plus y. Okay, so this is just the three conditions. The question is asking us to show that the sigma x plus y, so this is not a variance anymore because we don't have the square on the top of the variance, on the sigma. So this sigma x plus y is actually the standard deviation of the x plus y. The sigma x plus y divided by the sigma x plus sigma y. So these two things are also the standard deviations, okay? And the ratio between these two terms is smaller or equal to 1. Actually, this question is asking us to prove something. And we must start from the conditions, right? So the variance of x and the variance of y had nothing new. So let's work on this thing first. So the sigma square of the x plus y. Okay, just copy down this the condition. So the sigma x plus y square is actually the variance of x plus y. So by using the definition of the variance, this is equal to the expectation operator. So in this case, we do not need to worry about x and y are two random variables. Should I just consider the joint something, the joint PDF, joint CDF? Temporarily, no. Because this x and y are not totally separate in this calculation. The x is added on the top of the y. So x plus y, you can treat that to be a new random variable. For example, the z. If I'm asking you to evaluate what is the variance of z, we just use the definition of that variance to expand it. But this is the same thing. So actually, this calculation is just using the definition of the variance. So the definition of the variance is the expectation of something square. So what's inside of the square here? It should be the random variable itself minus the mean value, or in other words, the expectation of the random variable. In this case, as I mentioned, I temporarily treat the x plus y and plus y to be one single random variable. Okay, so this is the definition of the variance. So we are going to expand it. So actually, this part is equal to the expectation of x plus y. So I'm removing the first pair of the brackets. Okay, x plus y minus, for the second term here, the expectation of x plus y. This can be translated to ex minus the ey. And then for this whole thing, we square it like this. The next step. So I really want to just group the same terms together. So inside of the square operator, we have the x terms. We have the y and the y terms. So let's just reform this mathematical expression to group the same or similar terms together. So what we have is expectation of x minus ex plus y minus the ey. And then we square the sum of these two terms. Close the bracket. This is equal to the expectation. Now we call this as term 1, this is term 2. Term 1 plus term 2, and then square is equal to the term 1 square plus the term 2 square plus 2 multiple the term 1 and the term 2. And inside of this brackets, you can see we have three terms: term 1, term 2, and term 3. So let's just give the expectation operator to each of these three terms. So we have expectation of x minus ex square plus the expectation of the same thing, y minus ey square, and plus the expectation 2x minus ex y minus ey, then close the brackets. For each of these three terms, first term should be very simple. That is actually the definition of the variance of the x random variable. So this is actually equal to sigma x squared. For the second term, same thing, but for the random variable y here. In the third term, first of all, inside of the expectation, we have a number 2 here. We have that in such case, the expectation cannot do anything to this constant. So we can move this number 2 out. After you move the number 2 out, so let's just do that, okay? We are moving this number 2 out of the expectation operation. Inside of the expectation, we have only 2 terms left. One is x minus ex. The second one is y minus ey. The expectation of the product of these two things is actually calculating, okay, this is a new thing we learned from this week, is the covariance of x and y. Okay, I put a side note here. So what is the covariance of x and y? First of all, regarding notation, you can use the cxy to denote it. The same thing, but different notations. This is equal to the expectation of x minus the mean value of the x multiple the random number y minus the expectation of the y random variable. This is how we define the covariance. This co means we are handling 2 different random variables in the same calculation. Variance means naturally the covariance between 2 random variables have the similar meaning regarding the calculation. It's similar to that of the variance, but the only difference is variance is handling 1 single random variable, but covariance is handling 2 random variables. Okay, so this is just a set of notes we learned from this week anyway. And but how to move on to next step? Now we are going to use the second knowledge point. After reaching this step, it seems very hard to move on to next step. So now we are going to use the correlation coefficient rho xy to do some replacement. Can you recall how we define the correlation coefficient? We said in the lecture, the correlation coefficient rho xy is a normalized covariance. It is calculated, or it is normalized by using the covariance between the x and the y divided by the standard deviation of x by the standard deviation of the y. Okay, this is the first point we need to know, new in this week. And the second important point you need to understand is the rho xy correlation coefficient is a normalized covariance value. The reasonable value for the rho xy must be like this. Or if you do not like the absolute operation, this is equivalent with rho xy is in between -1 to 1. The same thing. We said if the rho xy is 1, so this means these 2 random variables have very strong linear relationship. So these x and y are highly correlated with each other, and their behaviors are the same. So one up, the other one must follow going up. One going down, the other one must going down as well. So this is the same behavior between 2 random variables, and the relationship is a strong linear between the 2 random variables when the rho xy is 1. If the rho xy is -1, that means Okay, the linear relationship is still very strong, but the behavior of these two random variables are opposite with each other. If one random variable going up, the other random variable value goes down, vice versa. Okay, if the rho xy is equal to 0, means these two random variables do not have any linear relationship at all. Got that? So this is about the correlation coefficient. So now we are going to use this knowledge to solve this step. Our concern is how to handle this covariance between x and y. By using the first knowledge point regarding the correlation coefficient, rho xy is used here. Now, what I want to do is to move the standard deviation of the x by the standard deviation of the y to the left-hand side. So in other words, okay, the first two terms remains unchanged. So plus 2. So regarding the covariance x and y is equal to the correlation coefficient multiple the standard deviation of the x and the y respectively. This result is good, right? Now let's use the second point. Rho xy maximum value is just 1. So at most, the highest possible value for the standard deviation, that's my fault. The highest value of the correlation coefficient rho xy is 1. Now, if this is 1, so we can see this rho x plus y square is given here, right? So rho x, so it's not rho, it's just the sigma x plus y square is this one, right? When we take the maximum value 1 for this rho xy, so the maximum value of the rho x plus y square is equal to sigma x square plus sigma y square plus 2 multiple. So now the correlation coefficient has already reached its maximum value 1. So we put 1 here. 1 by 2 is still 2. Then we just got rho x by rho y. This thing is equal to right hand side is so easy for you. That is rho, not rho, the sigma x and sigma y square equals rho sigma x plus y square max. So if we do the square root on both sides, so that sigma x plus y max will be equal to sigma x plus sigma y. Okay. But what the question is asking for? The question is asking us to show or to prove this relationship. So in this case, if we divide the sigma x plus sigma y on both sides, you can see equal to 1. But here we need to notice we have already using the maximum possible value for the sigma x plus y. So in other words, we can derive the final conclusion. Generally, if the maximum value of the sigma x plus y is not taken, then it must be smaller than 1 or equal to 1. This whole story. Okay, and then this question is solved. Okay, this is question number 1. So actually, in this question, I have already given you all the important knowledge points we need to know for this question, and some of them are really important. For example, how to calculate the covariance between two random variables, and what's the definition of the correlation coefficient. So, and what is the reasonable range of the correlation coefficient. So all these things are very fundamental, are very simple, but important for you to solve some questions. Okay, this is about the question number 1. So we have done that. Let's move on to the next one. In the question number 2, so let x and y be, okay, highlight the keyword, independent random variables with variance the sigma 1 square and sigma 2 square respectively. We consider the sum z equal to a by x plus 1 minus a by y, and a is between 0 and 1. So we want to find a which can minimize the variance of the z. So actually in this question, we have 3 random variables, x, y, and z. And we focus on how to determine the value of the constant a to minimize the variance of z. So let's just try to solve it. Okay, so let's find some free space. So let's, anyway, just keep going. Okay, so question number 2. So regarding this question, we have already known the new random variable z is equal to a by x plus 1 minus a by y. Of course, a is between, I think, 0 and 1, right? 0 and 1. Yeah, this is just all the conditions we have. And our focus will be how to minimize the variance of the z. Let's just work out what is the variance of z. The variance of z is, of course, VAR the z. By using the definition of the variance of z is equal to the expectation of something square, right? Inside of the expectation. So inside of the round brackets, we have z minus the mean value of z. Okay, again, this definition of the variance, very fundamental, and you must know this one very well. Okay, and this is equal to expectation. So again, so we are going to calculate the square of something within this expectation, and this gives us. Now I want to use our condition regarding the z to replace the z in this calculation. So we will have ax plus 1 minus a y. This is the so-called the random variable z minus the expectation of ax plus 1 minus a y. And we just want to repeat what we have done in the question number 1. Let's just group the terms. Okay, so what we have here is, so equal to ax doesn't change temporarily, and 1 minus ay doesn't change, and we put the expectation to each of the 2 terms. That is a by ex, the mean value of the x by a, right? And then minus 1 minus a ey. And then we close the brackets and square it, and then close another bracket. This whole thing. And in this whole term here, we have x term, and we have the y term. So put them together, so group them together. So this gives us the expectation something square. So for the x term, we take the a out, and then we have the x minus ex, this whole term, plus we take the 1 minus a out for the y terms, equal to 1 minus a multiple y minus ey. Now the whole thing becomes easier, right? So we have term a and term b, it's a plus b and then square. So let's just expand the square operator. So we got a square by x minus ex square plus 1 minus a square by the y minus ey square. Okay. And then keep going, plus 2 multiple a by 1 minus a by, sorry guys, this is really long one, x minus x by y minus ey, and then close the expectation brackets. Now let's just give the expectation operation to each of these three terms. So we got expectation of the a square and then x minus ex where are we? Square and close bracket plus the expectation of y minus a square, y minus ey square, and plus we move 2a 1 minus a out. Then expectation of the x minus ex by y minus ey. It's really long calculation. Okay, but next step should be simple, right? So we said inside of the expectation, the a square thing, the constant stuff can be moved out. So for this a square, we take it out and we put it at the beginning. And similarly, this 1 minus a square is also a constant, so we can move it out of the expectation operation. So we just need to amend this part. So we got 1 minus a square expectation of the whole thing. And the very last term is okay. So this expectation is actually giving us the variance of the x variable, because inside of the equation, you can see the x minus the mean of the x and then square. This is actually sigma x squared. Similarly, the second part is 1 minus a squared by the sigma y squared. Plus, this is constant. We just copy this here, 2a by 1 minus a. And again, this thing is now new to you because in the question number 1, we have learned this one. The expression of x minus the mean of x by the y minus the mean of y is actually calculating the covariance of x and y. So this is equal to, oh, sorry, not plus sign. It's actually the covariance of x and y. Okay, this is just the result we derived from this long calculation. Even though it's pretty long, but not very hard, should be pretty simple. And for this part, the first term and second term, we just stay like this. We can't move them too much. We can't make more changes on them. We should focus on this thing. 2a by 1 minus a. So this part is all right. We don't need to change that. What is the covariance of xy? The covariance is used to measure the linear relationship between the random variables, but based on the condition given in the question. So let's move that. Okay, we go back to our question. The x and the y, these two random variables in this question, are independent between each other. Independent means these two random variables do not have any relationship, including the linear one. So if we can read the independency between two random variables, so these two random variables must be uncorrelated. Uncorrelated. So in the video of lecture, I said uncorrelation means no linear relationship. Okay, so it must be uncorrelated. If they are uncorrelated between each other, so the covariance value between these two random variables must be 0. Okay, because they are independent, so they are uncorrelated. Because they are uncorrelated, the covariance must be equal to 0. So of course, if you want to evaluate the correlation coefficient, the rho xy, that's equal to 0 as well, as I mentioned before. And if the covariance between x and y is 0, so the very last term becomes 0. It's gone. So what's left here is a squared sigma x squared plus 1 minus a squared sigma y squared. So everyone please be reminded here, in the class, in the practical session, when we discuss the question here, I can explain to you verbally, so why this term is cancelled. But in the test and exam, I can't hear your explanation. So you can't just really cancel a term without any reasoning. So if you want to set this term to be 0, you must tell me why you set that to be 0. So here, we want you to give some explanations. Just like independency, it means uncorrelated. The uncorrelated means the currency is 0. So some things like this must be given here. So you need to explain the reason, not just the calculation. Okay, otherwise I will not be able to understand why you give this term to be 0. Okay. Okay, this is about our calculation so far. And what's the next step? The question is asking us how to determine the value of the parameter A to minimize the variance of the Z. So if you want to minimize the Z, the derivative of the variance of the Z with respect to that parameter A, which is under our control, must be equal to 0. Okay. So this is the way we want to make the variance of the Z to be minimized. Okay, so we want to solve that by using this way. But what is the derivative of the variance of Z? We just need to copy this term to this step. Just give us a square variance of x square, variance of x plus 1 minus a square by the variance of the y. In this case, everyone, please notice, our focus is how to control the value of a. So a will be our main focus, not the sigma x square and sigma y square. Regarding these given parameters x and y, the sigma x square and sigma y square has already been constants, so don't worry about them too much. Okay. So for this part, we need to just solve this derivative. So I think that should be very simple. We just need to do the derivative term by term. Regarding the first term, the sigma x square is a constant with respect to a, and the dA square over dt give you, I think 2a, right? So it should be reasonable. And for the next term, the sigma y square will be a constant, again, with respect to a, multiple, so 1 minus a square, then derivative. That give you 1 minus a first, and by 2, and by -1. I think this is right. Should be okay. So let's simplify this one. So sigma x squared by 2a plus -1. This gives us 2 sigma y squared by a minus 1, and we can group them. So this gives us 2 sigma x squared, which are constants, by a plus 2 sigma y squared by a minus 2 sigma y squared. So this is just a derivative of the, variance of z. So we reached this result. But for minimizing the a value, for selecting a value which can minimize the variance of z, so we need to make this derivative to be 0. So in other words, this whole thing must be equal to 0. And now, based on this equation, we can determine the a value. So a is equal to, we move this term to the right first. So 2 sigma y squared, then divided by, so regarding a term, so this and this will be extracted. It's just 2 multiple sigma x squared plus sigma y squared. 2 and 2 are cancelled. So the result is sigma y squared divided by sigma x squared plus sigma y squared. Then if the a value is equal to this one, the variance of the z will be minimized. Okay, so this is the solution to the question number 2. Okay, if you have any question, you can just discuss me in the second half of class. Okay. Okay, next one, question number 3. Okay, this question is pretty long. In the question number 3, we got a communication channel. The X random variable is the input to this channel. Of course, the random variable Y is the output from channel. So we still have 2 random variables, X and Y. So X input, Y output, like that. And for the random variable X, the possible values for X are just 1 and -1. So you can see for the X, we have -1 or 1, only 2 possible values. And the probabilities associated with these 2 values are 1/4 and 3/4 respectively. And for the output random variable Y from channel, the possible values of Y are corresponding to the input X with probability 1 minus P minus PE. So if the Y is equal to X, and if the Y equal to negative X, so the probability is P, or the Y value is 0 with the probability PE. Okay, now without reading the questions, let's summarize our conditions first. Okay, so let's find some free spaces. So here, so this is question number 3. For this question, I think sorry, the best way for us is to define a table. For this table, I want to summarize the so-called conditional probabilities. Okay, so the probability will be P that we got the output voltage, output sample Y is equal to the Yj when the input random variable is equal to Xi here. Okay, so this is the conditional probability. That means if we know we put the sample Xi into this communication channel, what is the probability that we receive the Yj on the output side of the channel? Actually, this is a very simple system. So this is your channel. X is input, Y is the output. So for the input X, it may have only 2 possible values, 1 and -1. Of course, we have the probabilities associated with 2 values. We don't talk about them right now, okay? Regarding Y, the possible outcomes are just X, -X, and 0. Okay, so if the input is 1 into the channel, so the output may be 1, maybe -1, maybe 0. If the input is -1, so regarding the X, the output Y may be -1, maybe 1, maybe 0. Okay, this is just the cases for this question. So what I want to do now is to evaluate such conditional probability. So if we know, okay, the input, for example, Xi means 1. So if I send this 1 into the channel as input for X, so I want to evaluate what are the probabilities for each of these 3 output values as Y. Okay, this whole story. So I think for solving this question, discrete cases, so we better to use a table to do that. Much easier and very clear. So row by row, they are the X values. Column by column, they are the Y values. Okay. Now, regarding the X value, that's pretty simple. We have only 2 possible values, 1 or -1, right? So regarding the Y, the values for the random variable Y's, So we have three possible values. They are 1, 0, -1. Okay. Now let's just go back to our question to examine the conditions again. So maybe we have forgot the details. The question is saying the output of the channel Y is equal to the input X with probability 1 minus P minus PE. So in other words, if I give an input X and produce the X as the output of channel, the probability will be this one. So this is actually saying, so where's our question? What's the sheet? Here. If the input is X, output is also X, for example, 1 in and 1 out. So the probability is 1 minus P minus PE, as mentioned. Similarly, if I put a -1 in and got a -1 out, the Y output is equal to X. So that case is also having the probability 1 minus P minus PE. And if the input, so I don't want to, anyway, just go back to the question condition. And if the input is X and the output is -X, the corresponding probability is the P only. So we go to our question sheet. So this means if I give the 1 as the input value of the X and produce -1 as the value of the Y, the probability will be P. Similarly, if I give -1 in and get +1 out, we got P probability as well. Okay, so we have done two columns, so only one left. So if you give the 1 as input and the output 0, such probability is PE. Similarly, if you give -1 in, output 0, the probability is also PE. Okay, this is just all the conditions we have. And the question number, part A, I think, of the question is asking us to determine the space of this experiment. We just need to list all the possible outcomes for this question, and the collection of all these comes give us the space of this experiment. So now I'm using blue pen for that question here. So because we have a pair of random variables, the values of this pair of random variables construct one single outcome of this experiment. So the space of this experiment should contain all the possible combinations between these two random variable values. For example, input X is 1 and the output is 1. So that means 1 in, 1 out, the first one. Or input is 1, output is -1. That means input 1, output is -1. Or input 1, output 0. Now we have done the cases for the input X is equal to 1. Now for next column, for next row, the same thing. If the input is -1, so output may be -1. Input is -1, output may be +1. And the input is -1, output could be 0. Then we have done all the possible combinations, and the collection of these 6 outcomes constitute the signal space, the space for this experiment. Okay, this is done, and I think the space is fine. Next part, and we have done the space, and please calculate the joint PMF, P X equal to X, Y equal to Y. In other words, we are going to evaluate the probability for each out of these 6 outcomes. Okay, so let's just do this one by one. That should be simple. So I change my pen to black, and then because in the collection of the outcomes, the 6 items, so we have to do them one by one. So I just give the index number of them. Okay, 1, 2, 3, 4, 5, and 6. So for the first case, we want to evaluate the probability that input x equal to 1 and the output y is equal to 1 as well. So this is the joint probability. So by using the Bayes theorem we learned before, this is equal to the conditional probability, which is x equal to 1 subject to the condition that y equal to 1. Using this conditional probability, multiple the probability of the condition. So in this case, y equal to 1 is condition, right? Yes, this is what I have done. Yes, this formula is right, but I don't think this formula can help us too much because we don't have such the value of such probability. We don't have the value for such conditional probability. So yes, right formula, but not helpful. So we can change the format of this calculation. In our approach here, we are using y equal to 1 as the condition, but we can just change our mind. This time, we can use the x equal to 1 as condition and put y equal to 1 at front. And then in this case, we are going to multiply the probability of the condition. The condition is x equal to 1. So this is really helpful because we have been given such probability in the conditional question. And for this conditional probability, we have done this in our table when we summarize all the conditions, right? So now let's use this formula to solve it, okay? Sorry for that. So now let's cancel this out. This formula is right, but not useful, so we cancel it out. And then we're using the second formula given here to solve the question. This is equal to, so we need to solve this conditional probability. That is the case where the input is 1 and the output is 1. So now for this one, we go back to our table. Input x is 1. So output y is also 1. The corresponding probability is 1 minus p minus pe. So here, we put 1 minus p minus pe here for that conditional probability. Then we multiply the second term, which is the probability of x equal to 1 event. But where we can find the value of it? Of course, from the condition of the question. So here, we have been given, if you want the value of the x to be 1, the associated probability is 3/4, so 3/4. So in other words, this value is 4/3. Then we can just copy that value 4/3 here. Then this is the first step. So what is the joint probability of our first outcome of the experiment? Then we can repeat this step for all other outcomes. So for example, for the second case, the probability that x is equal to, we just copy, okay? X equal to 1 and y equal to -1. That's equal to the same thing. Using y equal to -1 as front and subject to the condition that x equal to 1 multiple the probability that of the condition, which is x equal to 1 in this question. And for the conditional probability, so input is 1, output is -1. Input is 1, output is -1. The probability is p. So here we got p by what a stupid mistake. So it should be 3/4, right? 3/4. Okay, this is the second case. So for the remaining parts, so we just repeat these procedures again in the class, I want to skip this part. That's really too simple and you have known the procedures. I believe you can do that by yourself. Okay. So now we have done question 3A. Let's move on to the next part. Question 3B. So please find the probability of the event where the x value is not equal to the y value. X value is not equal to y value. So let's go back to our answer sheet. So regarding the part B of the question 3, we want to evaluate this case here. And then we may have a quick look in the table. Just remove this one, this one, this one. Remove this one. Okay. Now you can just see in the table there are only 6 cells. So out of these 6 cells, which one is indicating the probability where the x and the y are not equal? So here, in the first cell here, input is x, input is 1, and output is also 1. X is equal to y in this case. So we do not need to consider the first cell. And let's move on to the next cell on the right. Input is 1, output is 0. Okay, the input and output are not equal. So this should be considered in this case. And the next one on the right, same thing. Input 1, output is -1. They are not equal. This must be considered as well. In the next row, when the x is equal to -1, the first 2 cells should be considered because the output is not equal to input. And the very last one, input is x equal to -1, and the output is also -1. We do not need to consider them at all, right? But for this case, don't really just add up these 4 probabilities. That is not right, because all these probabilities given in these 4 cells are the conditional probabilities. But for this case here, this event can be converted to x equal to 1 and y equal to -1 plus x equal to 1, y is 0. And keep going, plus the probability x equal to -1, y equal to 1, plus the probability that x equal to -1, y is 0. What I want to say is, all these 4 terms are not the conditional probabilities. They are the joint probabilities. So it's why you can't just copy these 4 values from the table into the calculation directly. You still have to convert the joint probabilities into the corresponding product between the conditional one with the probability of condition. So let's quickly solve that. This is equal to p. So y is -1 subject to x equal to 1 by the probability x equal to 1 plus, now for the second term, you keep doing the same thing, y equal to 0, x equal to 1 by probability x equal to 1 plus, next one, okay, that's equal to summation of these 4 terms. For each of these 4 terms, it's just using the basis theorems to calculate the joint probability. Okay, quickly let's just solve that. Okay, for the first term here, the conditional probability is given at so x1, y is -1. So that's value here. So the probability, the conditional probability is p. Multiple for this px equal to 1, that should give us, I think, 3 or 4, right? Then plus for the second term here, x is 1, y is 0. So okay, we are going to use the PE here. So plus PE by 3 over 4. Then keep going plus. The next row here, x is -1, y is 1. So x is -1, y is 1. So the probability is p by 1/4. This 1/4 is the probability that x equal to -1. Okay. Then finally plus pe by 1/4. I think the result should be pretty simple. We just reform the terms and group the similar terms. P by 3/4 plus P by 1/4 give you P by 1, which is P. And for the other PE terms, which is PE. Then finish. I hope this is right and seems reasonable. Okay, this is everything we have done. And actually for this question, there may have another approach. So because question is asking you to evaluate what is the probability that x is not equal to y, actually this is equivalent to 1 minus the probability that x equal to y. And this x equal to y is also corresponding to the joint probability. So 1 minus p x equal to 1, y equal to 1, plus the probability that x equal to -1, y equal to -1. Then you still have to evaluate these joint probabilities and then do the calculation. I think the result should be the same. You may just go through that by yourself. Should be very simple. Okay. I think this is pretty much everything we have. If you have any questions, please just let me know. Okay. Okay, now let's move on to the very last part of the Okay, of the question number 3. Okay, let me try to enlarge it. Okay, very last part of question 3b is asking us to evaluate what is the probability of the event y equal to 0. In this question, you can see actually we have 2 random variables in the system, so x and y. But in this question here, we want to evaluate what is the probability of one single random variable out of 2. So here, so we start from here, okay? We want to evaluate what's p y equal to 0. So where's x? Okay, x is not shown here. So in other words, this question is asking us to evaluate the marginal marginal PMF of y and when the y equal to 0. In such case, from that table we created, if you want the output to be 0, so we just need to consider the medium column of the table, because only in this column the output y is 0. Okay, and let's go up. This is actually equal to the probability that x equal to 1, for example, what we output 0 as from the channel, plus the probability that we are giving the -1 as input, but produce the 0 as the output. Again, so this gives us y equal to 0, subject to x equal to 1 by the probability that x equal to 1, plus same thing, y equal to 0, x equal to -1 by the probability that x equal to -1. So for the calculation, for this conditional probability, so by checking our table, so in is 1, out is 0. So in is 1, out is 0. P for next row is P as well. So this gives us PE multiple this in here. The probability that x equal to 1, I remember that's 3/4, right? Plus for the next term, the second conditional probability is also PE multiple the probability that x equal to -1, which is 1/4. Result is just PE. Okay. Okay, everyone. So this is the question number 3. let's move on to the next question. So I think we are going to do the question number 4 now. So in the question number 4, we are considering the joint pair x and y. So x and y are two random variables. So the joint CDF of this pair of random variables are given below. So capital F, xy equal to, so two formulas. The first one is for x is greater than 0, greater than 1, and y is also greater than 1 case. Otherwise, its value is 0. Okay, this is joint CDF. Part A is asking us to show that in general, the marginal CDF fxx equal to the joint CDF where the y is equal to infinity. So let's just try the part A of the question 4 first. Okay, question number 4, part A. So in this part, we want to prove this is fxx, so this is marginal CDF of the random variable x itself, which is equal to fxy. So joint CDF, where the parameter is x, so x is still x, right? And then positive infinity. I think because we want to prove these two things are equal with each other, so let's just work out these two terms one by one. So I think the right hand side is pretty simple. Because so here let's focus on the right hand side. For the right hand side, we have already known the joint CDF of xy is equal to 1 minus 1 over x squared and 1 minus 1 over y squared when x is greater than 1 and y is greater than 1. So this is the first case, y equal to 0. Otherwise, so this has been given. So what we need to do now is just give the y value to be infinity. So that result should be for the right hand side term. Okay. So I just forgot to write x and y here. So what we can do is, by using this given condition, we are going to solve the fxy, the joint CDF, with x and infinity. This gives us, so this infinity means the y value is approaching to infinity. If the lower y value is approaching to infinity, the y value is definitely much greater than 1. So in other words, we do not need to consider the equal to 0 case. We just need to use the first formula to finish this calculation. And the result is, so very simple, 1 minus 1 over x squared. So this doesn't change because x is not changing. Multiple, keep going, 1 minus 1 over, this time y squared will be replaced by infinity square. Infinity square is also infinity. So 1 over the infinity is actually equal to 0. And 1 minus 0 for the whole thing is equal to 1. And finally, this 1 multiple the 1 minus 1 over x squared at front is just equal to 1 minus 1 x squared. So in other words, when y is approaching to infinity, this supported joint CDF is equal to 1 minus 1 over x squared. This result is the result for the right hand side term. Okay, we just keep that here, and then we are going to move on to the left hand side, like that. Anyway, for the left hand side, we are going to calculate the fxx. This is the marginal CDF for the random variable x itself. So here, I want you to notice this thing is not equal to integration fxy dy. So such kind of relationship is not true for CDF. Maybe you can say in the lecture you cite for the joint PDF or marginal PDF. So fxx is a marginal PDF of x is equal to integration. So the joint CDF, joint PDF dy from negative infinity to positive infinity. I learned this thing from your lecture. Why didn't you say it's not true for the CDF? Okay, you need to notice. In the CDF or joint CDF, one single value is indicating the cumulative probabilities up to from negative infinity up to this point. So this has already been cumulative probabilities. It doesn't make sense to do the integration to it again because one single value has already indicated the cumulative thing. So we are doing the integration to the accumulation. It doesn't mean anything. So this relationship, if you say this marginal one, marginal CDF is equal to this one. Sorry, this formula is not true. We don't have this relationship at all. But for the PDF, this makes sense because when you do the integration with respect to a PDF or joint PDF, this can be converted to the probability stuff. So this makes sense. Okay. Now the question is asking us, so left hand side of the equation. Okay. So what is the marginal CDF? But we can't use such wrong formula to determine that. So what can we do? Okay, now we need to use the knowledge we learned from the week 1. So the CDF of a vulnerable is actually equal to the integration from negative infinity up to x, then fxx. So the PDF of this vulnerable dx. So this is the formula we should use for this question. But then, if you want to use this formula, we got one more question. What is the marginal PDF of x? This is not given, right? Then another formula is needed to solve this marginal PDF of x, which is fxx, marginal PDF, right, of x is equal to, in this question, if we are able to figure out the joint PDF between x and y, and do the integration with respect to dy from negative infinity to positive infinity, we are able to eliminate the y from this joint PDF. Then, after eliminating the y, the remaining thing is x. That's the PDF of x. Okay, this looks like a good thing. Once we can evaluate the marginal PDF, this thing can be used here. And then we got another question. Again, what is the marginal PDF of the x and y? This thing is also not given in the question as condition. Okay, one more formula. So for calculating this the joint PDF, we can do the double partial derivative to the joint CDF with respect to x and with respect to y respectively, and then we should be able to derive this joint PDF. This joint PDF will be used here. Okay, now in this part, if we can do this double derivative to the joint CDF, we do this way. This is going back to the previous equation to derive the marginal PDF of x. And marginal PDF of x, maybe go back to the previous formula again and to evaluate the marginal CDF. So this is the idea of our work. So now let's just go through this. Of course, our first task is to determine what is the joint PDF. So we are going to do the double derivative, partial derivative to the x to the y. I think this part is pretty easy for you. So the fxy joint CDF has already been given in the question. So temporarily, don't need to worry about the equal to 0 case, because if the value of the joint CDF is 0, so the double derivative is also 0. So that's easy stuff. We temporarily ignore that part. Let's focus on the first part only. So when the x is greater than 1 and the y is greater than 1, so what is the fxy? So that should be 1 minus 1 over x squared by 1 minus 1 over y squared. Okay, so from this step, we are going to do the derivatives, but because of the limitation of time, so I'm not going to do that in the class. This should be pretty simple for you. Please do that by yourself. I just give the final answer. So for this part, after you finish the double derivative, the answer for this joint PDF will be 4 for x power to negative 3, y power to negative 3. Okay, this is the joint PDF. for these two random variables. Okay, this is the first step we finish. That is corresponding to this formula. Now, after we know this one, we need to target to determine what is the marginal PDF of x. So using the formula, the marginal PDF of x is equal to integration. So we want to use integration to remove the effect of the y, right? But in this case, because, so I'm happy to record that condition of the question, right? So when the x is greater than 1 and also y is greater than 1, so we have non-zero joint CDF value. So in other words, we should focus on the range of y, which is greater than 1, or in other words, from 1 to positive infinity. So in this case, for the lower boundary of the integration, we can just put the positive 1 here to positive infinity for the reasonable range of the y value. And for the joint PDF, it's just copy. So 4x power to negative 3 by y power to negative 3. And 4 by x power to negative 3 got nothing related to the y. So we move it out of integration. So we got this stuff. And this could give us 4 by x power to negative 3 multiple negative y power to negative 2 divided by 2 from 1 to positive infinity. And so for this part, calculation should be simple for you now, and we just give the answer now. Result should be 2 by x power to negative 3. This is the marginal PDF of x. This result is corresponding to, so go back, the second step given here. Sorry. Okay, the second step is done. So we have already known the marginal PDF of the x. So let's do the final integration to get the marginal CDF. Okay. So the marginal CDF of the x is equal to negative infinity to x, then the PDF of the x. So marginal PDF of the x. So 2x power to negative 3 dx. This is equal to same thing, because for a reasonable value of the CDF, so the start point of the x should be 1. So if the x value is lower than 1, so the corresponding joint CDF was 0, we don't worry about them. So here, in the next step, we change the lower boundary of the integration to positive 1. 1 to x, so 2 by x power to negative 3 dx. So this gives us the value. Let me think. It should be minus x power to negative 2 from 1 to x. Result is 1 minus 1 over x squared. Okay, this is the final sorry marginal CDF of x. So now we have derived this one as the final answer of the left hand side of the part A. So this result, 1 minus 1 over x squared, is the same. Where that? Okay, it's the same as the result we derived for the right hand side term. Because these two terms are equal, so we have already proved the part A of the question. Okay, so part A is done. From this question, we should realize one thing. Actually, if you want to evaluate the marginal CDF, you are not allowed to do this way. Sorry. Okay, so we should not do the integration of the CDF. It doesn't make sense. So you have to use the other information, like the marginal PDF or something like that, to determine the marginal CDF. That's the only way available for this question. Okay. Okay, part A is done. For part B, part B is pretty simple. So part B is asking us to, let me have a look, evaluate what is the fxx and fyy. So the marginal CDF for each of these two random variables. A really simple thing. So from our part A works, we have got the fx equal to this is or 0 otherwise. Okay, this is regarding the marginal CDF of x. So regarding the FYY, the CDF, the marginal CDF of the y variable, you can repeat what you have done in the part A to derive the marginal CDF of y. But for this question, it's very special because regarding this joint CDF, 0 is a small thing otherwise, right? And when the x is greater than 1 and y is greater than 1, the CDF, joint CDF is 1 minus square or cubic? A square, yeah. Multiple 1 minus 1 over y square. So this is the mathematical expression for the joint CDF. And you can see the two terms, one here, one here, one here. The format of these two forms are exact same, except the name of the variable. So if you are doing the procedure in the part A for the x, when you repeat the same procedure for the y, all the procedures are the same. You just need to replace the x by y. So here, we don't need to repeat this procedure again. We can just instantly write down the marginal marginal CDF of the y is equal to 1 minus 1 over y squared, which is the same format as the one given in the marginal CDF of the x. But this is true only for this particular question. For general questions, we should not do that. So when you try to determine what is the marginal CDF of the y, you need to repeat what you have done in the part A to solve it, to derive the answer. Okay, but for this question, let's keep that simple. Okay, just like that. So this is the answer for the marginal CDF of y, so which is for the part B of the question. Okay. Now let's move on to part C. In the part C, first of all, there are two questions in part C. The first one, we are going to evaluate what is the probability that x is greater than 4 and y. Hold on. No, sorry, my fault. The first question is asking what is the probability that x is smaller than 3 and y is smaller or equal to 5. This whole thing. Actually, this joint probability is actually the definition of the joint CDF, in which this x is this 3, this y is 5. So this is a very easy one. And also in this question, the number 3 and number 5 are all greater than 1. So for this question, what you need to do, you just use 1 minus 1 over x squared by 1 minus 1 over y squared. And x is equal to lower x, of course, lower x equal to 3, lower y equal to 5. So by substituting these two values into this equation, you got 1 minus 1 over 3 squared, 1 minus 1 over 5 squared. And then finish calculation, the result is 1 over 144. So this question is so easy, right? The hard part for the part C is the second one. I want you to evaluate the probability where the x is greater than 4 and y is greater than 3. So because we have the greater than for these two so-called events, we are not able to convert this one to the corresponding joint CDF directly. You have to think other ways to solve the question. Okay. Maybe some of you want to solve this one by using 1 minus the probability that x is smaller or equal to 4 and y is smaller or equal to 3. So I have to say this is incorrect. So let's quickly compare them. Okay. So for the left-hand side, let's draw this thing out. X is getting here, y is getting here. So I want to evaluate x is greater than 4 case. So 4 is getting here for x. So x is greater than 4 is this side of the area. Okay, to the right of the x to 4. For the y is greater than 3. Okay, 3 is getting here. So the y is greater than 3 is the area on the top of that part. So because I want the joint probability of these two cases, so these two events must happen at the same time. So the only region which can satisfy these two conditions is this yellow area. So only within this area, x is greater than 4 and y is greater than 3. This is the region corresponding to the left-hand side. Now let's have a look at the right-hand side. Okay, so leave it alone. So on the right-hand side, same thing, x and y are given here. So let's focus on this probability first. We want x to be smaller or equal to 4. Y is smaller or equal to 3. Okay, 4 is given here, 3 is given here. So let's draw the dashed line and dashed line. So x is smaller or equal to 4. That is the left part of, to the left of the x to 4, this line. And for the y is smaller or equal to 3. That should be the bottom section given here. And the intersecting region between the x smaller than 4, y is smaller than 3 is this yellow region. 3, 4, it should be this region. But don't forget, we have 1 minus this thing. Using the total area defined by the x and the y to minus this yellow area. So 1 minus that gave us this big region. This region here is 1 minus x smaller than 4, y smaller or equal to 3. But if you compare these two graphs, you can find the regions covered by these events are different. So in other words, this is indicating the left-hand side here is not equal to the right-hand side. Okay, they are not equal at all. So this approach doesn't make sense. But what is the correct way to solve the probability that x greater than 4, y is greater than 3? My approach is I want to use the Bayes theorem to convert this joint probability to the corresponding conditional probability multiplied with the probability of condition. So what I'm going to do is I keep the x plus greater 4 unchanged, but subject to y is greater than 3. Then multiply the probability that y is greater than 3. And then for the first term here, I can do, I copy this one unchanged. And then for the first term, because we are evaluating the probability of one single random variable event about x only, y greater than 3 is a condition, is known thing. So I don't need to include that in the evaluation of the whole thing. Okay, so we can treat that to be fixed temporary. So the evaluation of the probability of x greater than 4 is equal to 1 minus the probability that x is smaller or equal to 4. But of course, we put our condition here. So by doing this way, we are able to convert this greater than sign to the smaller or equal to this sign, which can be used later when we convert this one back to the CDF functions. Okay, but this is not the end. We have to keep going because we had the y greater than 3. So what I'm going to do is, regarding the first term, I'm going to do 1 minus. This time we got the conditional probability. I want to use the Bayes theorem again to convert that back to the joint one divided by the probability of condition. That is the probability of x smaller or equal to 4 and y greater than 3 divided by the probability of the condition. Then multiply the second term. The second term, temporarily we don't change that anyway, change the next step. This is equal to, now we need to start to process this term, y is greater than 3. We are going to repeat that basic theorem again. So this gives us 1 minus, okay, prepare long space. This doesn't change temporarily. This doesn't change, remains same. So on top of the fraction, for the joint probability, this time we are using the y, which is 3 as our main focus, and use the other term x smaller or equal to 4 as condition. Then multiple the probability of condition. Repeating that procedure again. So 1 minus doesn't change. P y greater than 3 temporarily do not change. Remains same. And this probability that x is smaller or equal to 4 doesn't change. So only for this part, we want to just convert this conditional one back to the ratio of the joint one divided by the probability of condition to replace it. So this gave us, so I change black color, okay? So this gave us the probability. Oh, my fault, guys, my fault. I didn't mean that. So I want to use 1 minus the probability, the y smaller or equal to 3, subject to x smaller or equal to 4, to replace this part. Okay. That's equals 1 minus, doesn't change, doesn't change, doesn't change. And for that bracket, 1 doesn't change, minus remains same. Now, for this part, I'm going to use the Bayes' theorem again to convert that to the ratio between the joint probability and the probability of the condition. So that's equals, on top should be the probability of y smaller than 3 and x is smaller than 4 divided by the probability of x smaller or equal to 4. Okay, almost done. First of all, you can see this term and this term can be cancelled, which is easy. And for this y greater than 3 probability, I'd like to replace them using 1 minus the probability that y is smaller or equal to 3. Okay, using this one to replace these two terms. The result will be 1 minus the joint probability. I think this is right at bottom of fraction. So it's 1 minus the probability the y is smaller or equal to 3, close the bracket, multiple another 1 minus p y smaller or equal to 3. Now, yes, we are reaching the end of question. So if you focus on all the probability terms in this equation, this one is corresponding to the joint CDF of the x and the y. Of course, x here, lower x is 3, lower y is 4. Okay, you know the fxy, the joint CDF mathematical expression, you can solve this number. That's easy. For this term and this term, they are the marginal CDF of the y when the lower y is 3. The same thing, fy 3. So in part B, we have solved marginal PDF of the y. Marginal CDF of the y. You can use the formula here. So after you replace these three probabilities with the numbers you derived, then you can evaluate the final answer. Okay, so the final result is 1 minus f. I think that we got 1 minus f x 4 minus f y 3 minus f x y 4 and 3. So I didn't really finish the whole question numerical calculation. You should be able to do that easily by yourself. So of course, you need to give the final numerical answer for this question, and you should be able to derive the numerical answer. Okay, so this is the approach to the question 4C. And actually, for question 4C, there is another approach. If you are able to, so still in the 4C, but the second approach. Actually, if you re-examine the joint CDF of X and Y, remember in the condition of the question, when the X is greater than 1 and Y is greater than 1, we know this is 1 minus 1 over X squared, 1 minus 1 over Y squared. And also in part B of the question, we got fxx equal to 1 minus 1 over X squared, and fyy, so marginal CDF of Y is 1 minus 1 over Y squared. If you examine these terms here, this thing is equal to this one multiple this one. So in other words, we are able to say fxy, xy, joint CDF is equal to fxx by the fy is the product of two marginal CDFs. This is a very good result. If you are able to derive such result, or if you are not for this question, okay, not for this question, you can derive such joint PDF relationships like this. Then from this kind of equations, we can say X and Y are independent between each other. I mean, if the relationship between X and Y have such relationship given the formulas, so X and Y are independent. If the X and Y are independent, the probability that X greater than 4 and Y greater than 3 is equal to these two things, X and Y, are totally no relationship at all. So this joint probability for such independent random variables is equal to the product of two separate probabilities for the two events, which is equal to 1 minus P X similar to 4, 1 minus P X as Y similar equal to 3. This is CDF of the X, this is CDF of the Y, so marginal CDFs, of course, is 1 minus Fx 4, 1 minus Fx again Fy 3. This thing and this thing have been solved in part B. So just give the values X equal 4 or Y equal 3 to solve that. So result is 1 minus Fx 4 minus Fx 3 plus Fx 4 by Fy 3. So this result remains the same as the one we derived in our approach 1. Where that? Okay, guys, sorry, a typo here. This plus. Okay, but anyway, small thing. And yes, these two results are same. But I think that the second method is much easier than the first one. But if you want to use the second methodology for this question, first of all, X and Y must be independent. Secondly, you must be able to recognize X and Y are independent. If you can't do either of these two conditions, so you have to use the first methodology to derive what we want. Okay, this is about our question number 4 of the tutorial 2. So in the next part, the question number 5 up to the question number 5, 6, 7 will be your homework. Please just try them out by yourself, and the answer and solutions of the questions will be given maybe tomorrow or on Saturday, and you can find them on MS. So next part, in this class, we are going to have a look at the question number 6 of the tutorial 1. Okay, this is the class of last week, because during the consultation, I received some questions from students regarding that question. And that question is pretty important. So I want to give you the details regarding the question. So next part, we are going to go back to the tutor 1 and start the discussion of the question number 6. Question number 6 of tutor 1. Okay, so for the part A of that, we want to evaluate what is the CDF of the random variable y. So that's equal to the probability that y value is equal or smaller than the given parameter lower y. For such event, y value is smaller or equal to the given parameter y. We can assume this y value, the lower y value, is here. Okay, this is the point along the random variable y axis. So we assume the parameter y is given here. So if you want to evaluate what is the probability that capital Y is smaller or equal to this lower y, actually we want to evaluate the probability that y value fall into this region along the y-axis. And also, because we have already known the deterministic relationship between y and x, so a single point on the y-axis must be able to be mapped to the x points. For example, if you think about this y point, this single y point, lower y point on the y-axis can be mapped to the corresponding x1 and x2, these 2 points. This can be mapped for all the y points to the corresponding x points. In other words, the evaluation of such event is equivalent to the evaluation of the probability that the random x value fall into the x1 and x2 points. So these 2 events have the same or equivalent probabilities because the relationship between the y and the x are fixed, are deterministic. And if we have already converted these to the x probabilities, so we can use knowledge of the x random variable CDF to solve that. So this is pretty simple. This is equal to fx x2 minus fx x1. Okay, almost done. Almost done. There's only one thing left. Because our target is to determine what is the CDF of y. So when the CDF of the y is evaluated, we are using y as the parameter. But after we finish this mathematical induction, on the right-hand side, so far, we have the x2 and x1. We don't have this y parameter at all. This doesn't make sense. So in other words, we must find a way to represent the x1, x2 in terms of y. Now let's double check our plotting. X1 point is here, X2 point is here. And the relationship between the X value and the Y value are given by these 2 segments. So if we focus on X1, so based on the Y equal to the negative X, so this X1 value is actually equal to negative Y. Similarly, if you focus on the X2 value on the right-hand side, because that line segment is fixed, so this x2 value is equal to a positive y. By using this knowledge, so regarding these 2, CDFs of x, that's equal to fx. So x2 is positive 1 minus the fx. This time for x1, we got negative 1. Then finish. Okay, this is about how to evaluate the CDF of y based on knowledge of the CDF of x and also the relationship between y and x. Part A is solved. Part B. In part B, we want to evaluate what is fy y. Of course, based on our knowledge regarding the fxx and y equal to x absolute value, these 2 conditions are known. Regarding the question, we still have to just plot that thing out. So x are given here, y is given here, and the relationship is fixed like this. So y equal to x absolute value. And in this case, because our focus is the PDF of the y, so I want to evaluate fy y multiple the dy. So this thing is actually evaluating the probability that y value is falling into y plus dy and to the y. So within the small y direction increment, what is the probability that y fall into this small segment? Graphically, this thing is actually within this small segment. So we assume along the y direction, this is dy. So from the y point to y plus dy. So I'm going to using this thing to evaluate what is the probability that the random variable y fall into this small red color segment. Same thing as what we have done in the part A. This small segment dy can be mapped to in this question, two small segments dx1, dx2. Again, this is totally because the y and x relationship is determined and fixed by this relationship. So in other words, mathematically, such probability or the PDF by dy is actually equal to fx x1 by dx1. For this question, because there are two small segments along the x-axis, so that's plus fx x2 dx2. So actually, I'm evaluating the probabilities. This term is the probability that x fall into x1 to x1 plus dx1. This is the probability that x fall into x2 plus dx2 and x2 region. Okay, now you can find the relationship easily, right? So actually, the most important thing for such evaluation is the equal of the probabilities. Okay, now let's focus on this case. Our final target is to determine what is the PDF of y. This dy seems to be a little bit redundant to this final target. So let's divide dy on both sides. So this equation is now changed to fy y. So this is the one we are after is equal to. So fx x1 remains unchanged, but dy is moved from left to right. So dx1 over dy plus fx x2 dx2 over dy. So everyone, so here I want to remind you one thing. We are evaluating this thing based on the probabilities. So regarding the probabilities, we don't have negative thing. All the probabilities should be the value between 0 and 1. They're all positive. But once you divide dy on both sides, this thing could be negative because this is kind of the gradient of curves, right? And this could be negative. We don't care the signs because all the probabilities are positive. So here we are going to add absolute values to this one to convert them back to positive because we want to know the value of the probabilities only, nothing about the gradients. Okay, so this whole thing here, and there we need to go one more step further. I don't like dx1 over dt because I know the function of y equal to x absolute value. So I like dy over dx, not the other way around. So because of that, so I turn this thing and this thing upside down. So we got fx x1 divided by dy over dx1 absolute value plus fx x2 divided by dy over dx2 absolute value. Okay, close that. Okay, there's only one more step left. So what is it? What is it? This thing is actually the gradient of the y function curve at position x1. This is the gradient of the y function at position x2. So let's go back to our graph quickly. So, okay, this point is x1. At this x1 point, regarding this curve, what is the gradient of it? Okay, its gradient in this graph, in this question, is -1. And at position x2, what is the gradient? Gradient is +1. So these two values can be derived from the graph easily. So in other words, this is equal to fx x1 divided by absolute value of -1 plus fx x2 divided by the absolute value of +1. The two gradients at x1 and x2 of that y function. Okay, but you have the absolute values, so both of them are 1s. So we cancel them. Result is fx x1 plus fx x2. But we have the same issue again. This PDF of y is a function of y, but after we finish these mathematical inductions, we got x1 and x2 only. So you still have to use the y to represent the x1 and x2. So that's have been done before. So we just use the result. Okay, that's equal to fx -y plus fx +1. So I think this answer to the question number 6 of the tutor 1. So now, guys, everyone, so we stop recording here because we have done this explanation. 1 second, please. Stop.